Okay, so now we're going to look at how temperature changes affect the equilibrium position for a system in a state of equilibrium. Okay, so we're going to look at how raising the temperature will affect the equilibrium. And as you can see the statement here, it says that raising the temperature of an equilibrium mixture shifts the equilibrium in the direction of the endothermic direction, while lowering the temperature shifts the equilibrium in direction of the exothermic reaction. Now, in order for us to understand this, we have to, of course, apply Le Chatelier's principle, and we also can take a particular point of view where we treat heat as a product of a reaction, just like any other chemical product, or and that would be the case of an exothermic reaction, because if you remember, when you have a reaction that's exothermic, heat is produced, right? So we can treat heat as a product. On the other hand, in an endothermic reaction where heat is being used up, we can treat it as a reactant, all right? So in other words, we can represent an exothermic reaction. Whoops, let me get my, okay, let me get my pen function here. We can treat, let's say the reaction is exothermic. Let's say it's A plus B, or A going to B, I should say. Then we can simply add heat here on the right side, treating it as a product, right? So that's an exothermic reaction. On the other hand, in an endothermic reaction, it would be A plus heat to give product, all right? Because the heat is being used up, so we can treat heat as a reactant, all right? So remember, in an exothermic reaction, heat is produced, so you write heat on the right side. In an endothermic reaction, heat is being absorbed, so you write the heat on the left side of the equation, all right? So if you think of it in these terms, then you can understand what all this was saying, right? If you, for example, increase the temperature, let me squeeze this down here. Let's say the reaction is exothermic, so A to B plus heat, right? That's the exothermic reaction. And let's say you increase the temperature, right? If you increase the temperature, that means that you're adding heat to the system. Whoops. Adding heat to the system. And if you're adding heat, that means that according to Le Chatelier's principle, that's a stress that you are applying. So the system will try to reduce that stress by shifting in this direction. So it will shift in the endothermic direction, and therefore, so there, let me just write here. So therefore shift to the left, and therefore the concentration of A will increase while the concentration of B will decrease. All right? So that's what happens in an exothermic reaction where you increase the temperature, the reaction will shift in the direction using up the heat that you'd have added, and therefore the amount of reactant would increase and the amount of product would increase. On the other hand, if you were to decrease the temperature, then the reverse or converse argument will hold. If you decrease the temperature, that corresponds to a removal of heat, which means that the shift will now move to the right, and therefore what that means is that the concentration of A would decrease and the concentration of B would, increase, all right? So that's basically what happens when it comes to temperature changes. So in order for you to predict the temperature changes, right, or the effect that the temperature changes will have on equilibrium, you have to look at whether or not the particular reaction is exothermic or endothermic. That's the first thing you look for, and then you start making your arguments and arriving at the correct conclusion in the end. Okay, so that's as far as temperature changes are concerned. Now, as far as catalysis is concerned, there's nothing much to say here because, as stated here, the catalyst, as we know from the previous chapter in kinetics, lowers the activation energy of the reaction. What it does in the case of reversible reactions is that it lowers the activation of both the forward and reverse reaction, right? So therefore, both the forward and reverse reaction will increase in rate to the same extent. The consequence of that is that the equilibrium state will remain the same, all right? So basically, adding a catalyst does not shift the equilibrium position one way or the other. Basically, it allows for the equilibrium to achieved at a faster rate. And that's all we can say as far as the effect of a catalyst would be on an equilibrium system, all right? Okay, we're going to stop here because the next couple of slides will have some that I want us to work through.